Alright, so we built an autonomous reconnaissance robot, or natural disaster robot. It has a couple sensors that measure temperature, carbon monoxide, and smoke, and it autonomously drives via GPS and compass outside. We can't really show that to you today, but it also has obstacle avoidance sensors on the front. They're used time of flight sensors. They're like a LiDAR laser sensor. Yeah, and it drives around.
Yeah, there's 3 main modes that are controlled from this RC controller: off, RC control, and autonomous. We kind of use this as a safety feature so that if you're like about to run into something because the algorithm doesn't work or something, you can turn it into a RC mode. Kind of a proof of concept. If you attach it to a camera, you could have this drive and kind of have a camera feedback to something, for example. There's lights that work. So you can go in the dark. They're super bright, so we can turn them off.
And we also have an LCD screen on the top. I don't know if you can see that. Once a second it refreshes temperature, and it has carbon monoxide as well as smoke in parts per million.
And those sensors can be swapped out. We have a 9-piece set, so we've got 7 other sensors that can be plug and played in there depending on what you're trying to sense.
Yeah, flammable gases, methane, hydrogen, anything of that sort. You can also sense. Those are these sensors right here are.
Light. All the snow. Yeah. It'll go up. So it's pretty strong. We're using 6 DC motors. All 6 are controlled by 2 BTS motor drivers that form a full H-bridge when connected. All of the motion, object avoidance, GPS, and compass are controlled by a single Arduino. The LCD and LED output and the sensors are controlled by a separate Arduino. So we have forward, reverse, turn right, turn left. And I wrote the software so that the obstacle avoidance algorithm uses the same functions that the RC mode does, just to avoid code redundancy. So also made sure our wiring was correct in RC mode.
We made the chassis out of some aluminum C-channel as well as just some carbon fiber that was donated to us for a top plate and a bottom plate that we can screw through.
Before we do that, it does have, running through PIC, we have a tilt sensor that will let the user know if it happens to go above roughly 90 degrees, so if it flips itself over. It also is tied into the motor controller, so it will stop all motion if it goes upside down.
You want to just do that while it's running?
Yeah.
I'm still holding the throttle.
Yep.
So just a simple safety feature we wired in.
And as Zach said, we made it out of aluminum C-channel that we mitered and had a friend of mine weld up. I built a jig to actually do all the holes for each of the 6 individual motors so that we could actually direct mount everything. Unfortunately, it does have a slight alignment issue and pulls to the left, which you will see in the compass video, which causes some slight issues, but it's pretty good.
So the main thing, I'm going to take this battery, I'm going to unplug it and take it out, so just other stuff that's available. So we have our 6 motors right here, controlling all motion. Both of the motor drivers are right here. All of the motor wires are spliced into those motor controllers, so all 3 motors are controlled by each motor controller, forming a full H-bridge. We have a power rail right here that's connected to a voltage regulator. So we go from 12 volts down to 5 volts, and all of our wiring is done into that power rail. Our main Arduino is here that controls all motion, and our second Arduino is here for all of the user input and output.
Yeah, and the PIC is hidden right around here. I can see it.
It's way back in the chassis.
there.
It's tucked deep against the chassis.
Yeah, and we also custom built our battery from recycled batteries.
This is our first robot, just a kind of a proof of concept. So the goal with this was to be able to go around any obstacle of any size. So we wanted to be able to sense when the obstacle was done being near. So the front sensors detect where it is, and then there's a sensor on the left side that detects while the obstacle is still there. So that was like kind of the first generation of our avoidance algorithm using our TOF sensors. We then went to this model. So it doesn't turn perfect 90 degrees, but it's using logic to tell which sensor has greater distance in front of it, and then turning left or right. It's obviously still kind of dumb and doesn't really know where everything is because it's not perfect, but it definitely doesn't hit anything and goes around stuff effectively. We couldn't get the compass to tie into the TOF sensors inside because there was so much interference in this building. But we were able to work to get our GPS and compass to work together to guide the robot. You can see our controllers on there, so we have proof that we're not actually steering any of this. But it's turning left to get all of the compass data in a full 360, and then once the compass and the GPS are within 25 degrees, they'll go forward for 1 second and then refresh. Yeah, so the post is there just to get the compass away from the interference from all of the motors, the battery, all the electronics and metal. Just because we were running into so many interference issues, we figured that was the easiest way to do it. And so this turn left function is the same turn left function from the RC. And it's just turning left until the GPS and the compass are within a tolerance